Welcome to the 48th lecture on computational mathematics with SageMath. In this lecture, let us explore some methods of numerical integrations using SageMath. So, we have already seen how to find integral of a function. So, let us say for example, if you look at integral of sine x cube into e to the power minus x square from 0 to 1, if you try to evaluate this integral using this integral function in sine, it will actually give you no output. It will just return the same command which you are giving, because it is unable to, Sage is unable to compute this integral symbolically or explicitly. So, what you can do is you can use numerical integration. We have already seen this whenever you Sage is unable to find integral, definite integral explicitly, then we can use numerical integral. So, Sage already has inbuilt function to find numerical integral. So, let us write this. So, in this case, integral of sine x cube into e to the power minus x square from 0 to 1, the value is this is the integral and this is the error term. So, numerical integral also gives you error when this integral is computed. Now, of course, you can take help on this inbuilt function numerical integral, go through that document and then see how this function is created in SageMath, right. So, let us take an example, another example. Suppose we want to find integral of x plus sine x square plus 1 between minus 1 and 3. So, of course, Sage has inbuilt function, using that we can compute the integral. In this case, integral is 9.08383 and so on, with error or tolerance limit as 10 to, of the order 10 power minus 13. Now, let us try to create our own user defined functions using two methods. One method is trapezoidal method, that is trapezoidal rule, and the other one is Simpsons 1/3 rule. So, how do we do that? So, in case the idea of finding this numerical integral is to approximate this function integrand using interpolating polynomial. So, we can use interpolating polynomial of degree 1, that is linear function, or quadratic interpolating polynomial or cubic interpolating polynomial, and one can also use spline interpolating polynomial. So, that is the basic idea. Trapezoidal rule uses linear interpolating polynomial, whereas Simpsons rules uses Simpsons 1/3 rule uses quadratic interpolating polynomial, and Simpsons 3/8 uses cubic interpolating polynomial. So, let us start with trapezoidal rule. So, what is it? So, this is the function, the graph of this function. You want to find the area under this curve between x equal to minus 1 and x equal to 3. So, what we do, we approximate the curve by means of a straight line, that is linear interpolating polynomial. So, when you do that, when you do that, then this is what you will get, right. So, this is the original curve, this is the straight line passing through these initial point, let us say a comma fa and b comma fb. However, if you integrate this, you can see that this is the extra portion, this is extra portion, this is extra portion, this is extra portion. So, a lot of error is there. Now, instead of the whole interval approximating this function in the whole interval by one single linear interpolating polynomial, now let us divide this interval into two equal parts. So, if I divide into two equal parts and then see what happens, then the value of the integral you are splitting into this part and then this part. So, you will see that the error would have reduced, and instead of two parts, suppose if I take 10 parts. You divide this interval into 10 equal parts, and then in each sub interval you approximate the function by linear interpolating polynomial, and by that join the endpoints by a straight line, and then you can see here this area of this sum of this trapezium, that is these are all trapezium, that is why it is called trapezoidal method, is much closer to the actual area between this curve. Instead of 10, let me make it 30, and then you will see that it is much closer, right. Instead of 30, if you make it for example 100, then you will see that the actual area is very close to the approximate area. Now let us look at what happens. So suppose we obtain this interpolating polynomial, we fit this interpolating polynomial to these points a comma fa, b comma fb. So fa and fb I am just defining as variables, and px is a polynomial which is equal to x minus b upon a minus b into fa plus x minus a divided by b minus a upon fb. So this is actually a Lagrange interpolating polynomial passing through 2 points a comma fa, b comma fb, and then if you integrate this and then ask it to simplify the integral in this case. So actually in this case integral is going to be half into half into the base, that is b minus a into the sum of this parallel height, that is fa plus fb. So it will be half times b minus a into fa plus fb, right. That is what it would have reported. Yes, this is minus half into a minus b if you multiply, push it inside, it will be b minus a into fa plus fb. So that is the area using single interval. If you divide this interval into n equal sub intervals, so if you divide this interval ab into n equal parts, let us say first part is x1 x0 to x1, second part is x1 to x2, and so on, last part is xn minus 1 to xn, then the sum of the area of this is going to be equal to sum of all these areas. So first part is h, where h is the length of this sub interval, each of this sub interval. So h by 2 into f0 plus f1, next one will be h by 2 into f1 plus f2, and so on. Last one will be h by 2 into fn minus 1 plus fn, where fn fi is f at xi, h is the b minus a upon n, and if you add all these things, the except the initial f0 and fn, all will come twice. So this is what is called composite trapezoidal rule of numerical integration. So let us create a user defined function for this. It is quite simple. So I am giving the name composite trapezoidal. You input f, the function, the endpoints a and b, and the number of sub intervals, the number of intervals to which you want to divide this, right. So h is equal to b minus a upon n. Let us create this sum, I will call that as my sum. So initially my sum is h by 2 into f naught is f at a, and then for the remaining it is add all these f1, f2 and fn. So that is what is added here, and then at the end you add half of fn. So here instead of half of fi for I between 1 and n minus 1, we are just taking fi. So this is f naught by into h by 2, the remaining is f1 by f1 times h, f2 times h, and fn minus 1 times h, and the last one is fn. So and then let us return this, let us run this, and let us now call this function and find integral of sine x upon x between 1 and the Euler number e using composite trapezoidal rule, and let us take 10 intervals. Where, and in case you obtain this integral using inbuilt function, this is what you get. So this is 0.874957 actual value, and this case 0.8747. So it is not very far, even 10 intervals has found using trapezoidal rule quite close to the actual value. So instead of 10, if I make it, for example 20, then this will be much closer to this actual value, or if I make it 50, these two will be much more closer, right. You can even tabulate what is the error term in each of these iterations. So, for example, we are taking the n, the number of interval as 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 7, 2 to the power 9, and find out the value of the integral using trapezoidal rule, and find out the error term, which is the absolute value of the integral computed using trapezoidal rule, and the exact integral. Exact integral in this case is the numerical integral of fx from 0 to 1, or you can write numerical underscore integral, both will work. So, let me tabulate this error. So, you can see here for n equal to 2, the error is quite large, for n equal to 4 it has reduced, and so on. For n is equal to 128, error is of the order 10 to the power minus 6, and for 512 error is 10 to the power minus 7. So, the error is decreasing. Of course, this the order of this error is not very high. So, this trapezoidal rule, it is very simple rule of finding numerical integral, but in this case error is the convergence is a bit slow, right. So, now let us look at Simpson's 1/3 rule, and in this case we approximate the function by quadratic interpolating polynomial. So, let me look at what is this interpolating polynomial. So, this is what you have. If you divide this in, so if I want to fit quadratic interpolating polynomial, we need 3 points. So, what we do with between a and b, we divide this into 2 equal parts and take these 3 points, this and these 3 points. Let me reduce the figure size so that it will be okay, this is all right. So, and then we fit Lagrange interpolating polynomial, quadratic interpolating polynomial to these three points. In this case, what we have done, this is the Lagrange interpolating polynomial fitted to the points a comma fa, b comma fb, and c comma fc, where c is the midpoint of a and b. So, this is quite simple Sage routine to plot the graph of the function along with the fitted interpolating polynomial, quadratic interpolating polynomial, and it is shading the area under this interpolating polynomial, right. Now, let us look at, we increase this number of subintervals. So, suppose we increase, instead of dividing into 2 equal parts, let us divide into 4 equal parts. Of course, in this case number of parts will be required to be even. So, in this case when you try to, just a second, basic Simpson plot I have called, yeah. So, Simpson plot, what happened, oh, Simpson plot. Yeah. So, in this case now you can see here we divided this interval into 4 equal parts. So, this is the first 2 parts. So, we are fitting interpolating polynomial between these 3 points, this and this, and then next we are fitting interpolating polynomial between these three points, and so on. So, now instead of 4, let us make it 10 equal parts, and in this case now you can see here the value of the integral, actual integral and approximate integral will become much closer, and instead of 10 parts, let us make it 30 parts. So, we divide into 30 equal parts, and yeah. So, what you have to do when you have divided into 30 equal parts, you take first 2 parts, and in that you fit a quadratic interpolating polynomial, take the next part, fit the quadratic interpolating polynomial, and so on. So, now let us look at what happens to this integral. Suppose, so first approximation was, if you divide this interval a b into 2 equal parts, a b and c is midpoint of a b, and then when we fit this polynomial and try to find out. So, this is the polynomial, quadratic interpolating polynomial, and then integrate this between a and b, and then if you try to simplify, this gives you minus 1 by 6 into a minus b, which you can thought of as b minus a divided by 6 into fa plus fb plus 4 times fc. So, 4 times fc. What is it? Let me make it 1 here, so that, okay, so yeah, no, this is 2. So, this is what you have. So, this area under this fitted cubic you are plotting, and this is your FA, this is FC, this is FB, this height is FB, and what we have obtained this, in this case, area is given by, when you approximate this function fx by quadratic interpolating polynomial, the area under this quadratic interpolating polynomial between a and b is given by 1 upon 6. So, now 1 upon 6 in this case the length of each interval is half b minus a. So, b minus a upon 6 can be thought of as h by 3, where h is the length of this each subinterval, that is b minus a by 2 in this case, plus fa plus fb plus 4 times fc. Now, when you add these, now when you for example divide this into 4 equal parts, now what you have to do is you need to add this portion and plus this portion. So, what will this portion, the area under this portion is going to be h by 3 times f at a, or let us say f at x naught plus f at x 2 plus 4 times f at x 1. The next one will be f at h by 3 times f at x 1, sorry, f at x 2 plus f at 4 times f at x 2 plus f at x 4, f at x 3 in this case. So, this is x naught, x 1, x 2, x 3, x 4. So, this will be h by 4 times f 0 plus 4 times f at 1 plus f at 2. Next one will be f at h naught by 3, h by 3 into f naught plus 4 times f2, not f naught, it is f2, this is f3 and this is f4, right. So, if you add all these things together, you get what is called composite Simpsons rule. So, composite Simpsons rule. So, integral of fx from a to b, if you are dividing this interval into n equal parts, this is equal to x naught to x 2. If you are dividing into 2 equal parts, x naught to x 2, this is equal to h by 3 into f naught plus 4 times f 1 plus f 2. And if you generalize this, that is when you add this, divide this interval into n equal parts, then how will you, what will be the integral, approximate integral? You integrate this approximate interpolating polynomial from x naught to x 2, then from x 2 to x 4 and so on, xn minus 2 to xn, add all these things. So, when this gives you a formula h by 3 into f naught plus 2 times all the even fi's plus 4 times all odd fi's, and then last one is fn alone. So, this is what is called Simpsons 1/3 rule or composite Simpsons 1/3 rule. So, now let us write a Sage routine for this. Again, it is quite simple. First of all, this number of interval has to be even. So, in case it is odd, you just throw an error saying that n should be even and h is b minus a by n, and then declare my sum as fa, which is f naught here, and then add whenever I is divisible by 2, you add 2 times, this is 2 times. If it is not divisible by 2, then add 4 times, and then last one you add fa, and then whole thing you divide by, multiply by h by 3 and return the numerical value of this. So, now let us call this function, and in this case but 10 interval it has got this value, and actual integral is 9.0838, and you can see here. So in case now instead of 10, if I give 200 is quite large, 20, then you can see here these two integral are also much closer. And again you can tabulate the error term, and one can show that the error term in this case is much smaller. So Simpson's 1/3 rule will be actually much better than that trapezoidal rule. So you can see here in terms of 4 interval itself, the error is 10 to the power -6, and it is decreasing quite rapidly, right. So similarly you could use SciPy in order to compute numerical integral. So how do we do that? Inside SciPy there is a integrate function, integrate module, and inside that you have option sims for Simpsons and trapez for trapezoidal rule. So let us look at, I have this function fx equal to 1 upon 1 plus x square, and if you want to integrate this, let us say take n equal to 32, then what do we do? First we need to find out what are these x values, and then call this trapez fx over these points x. So this is what we get using trapezoidal rule and using inbuilt SciPy function trapz. Similarly you can use sims this, right. So you can use either SciPy, or you can use you can create your own function. So there are many other methods of finding numerical integral, and for example you can use, instead of 1/3 rule, you can Simpsons 1/3 rule, you could use Simpsons 3/8 rule, which uses a cubic polynomial to approximate the function in a given interval. So in that case you will read 4 points in order to fit a cubic interpolating polynomial. So I will leave that as an exercise. Write a Sage routine to find numerical integral using Simpsons 3/8 rule, and hence use this routine to evaluate this integral by taking n equal to 30. In this case the n has to be divisible by 3, and similarly evaluate this integral from 0 to e of e to the power x square using Simpsons 3/8 rule and Simpsons 1/3 rule. You could also again tabulate the error term, right. There are many other methods actually, for example Gauss quadrature formula and other things, etc., but we will not look at all these methods. I am sure you should be able to write Sage routine for any of this numerical integral method which you have learned. So let me stop here.